Yep.
Excellent. So you got my email from yesterday, I trust. There's 67 of us. Well, maybe even less now. It doesn't really matter. This is a good number of people. Um, there's a few announcements, two of them really that I have to make. One is I've been discussing with physics how this course is progressing. They're the leaders, of course, because the research is going on there. We're just building up our quantum computing research faculty slowly here in CS. Now, have you all heard of Slack? Slack is an application, a collaboration application that we've been using, and we're very interested in your weekly constructive criticisms. So we want you to be involved, you as a class. We'd like your individual comments on a weekly basis, and you can use Slack for that. What I'll do is eventually, as soon as it's set up, I'll send the URL to you, and you can use that at any time as a sort of a forum of opinion. And those opinions, I don't know, I think we can make them anonymous, but it's more that we would like to see how you think the course could improve. Remember, these are extraordinary circumstances. Don't forget that. One is that this course is eventually going to be the second course, and you're supposed to have already had the mathematics, and you're going to get a break for that. Obviously, you're also getting a break in terms of the fact that this is COVID-19, online, etc. So you survivors will prevail. You will make it through. You have my word. As long as you do you put in some effort. You have to put in some effort. Also, I think it's only fair that I send out some examples of the kinds of midterm questions I'll be asking. I'll set those up as soon as possible. Are there any questions? Okay.
No, seems straightforward.
Okay, then. I just thought I'd go back to this slide before we finish this first PowerPoint. I added this image here of a so-called block sphere. This is the way we we'll get into this actually next week, the details of how you derive this thing. But what it is a visual representation of what a qubit looks like. And so you can see it has this basis state, never mind this funny notation for now, but that's basically 0. And here, orthogonal to it is 1. And you may say, what do you mean orthogonal? It lies along the straight axis. Well, that's because the block sphere is a 3-dimensional projection from a 4-dimensional space. And so you can see everything here is bizarre. Don't worry about that. The fact of the matter is these really are orthogonal, but this is a projection from 4 dimensions. Why 4 dimensions? Because it's C cross C. That's the space we're working in, where the complex plane is already 2-dimensional. So clearly, when you deal with qubits, they're 4-dimensional entities. We'll get into that later. But the point here is, and there was a little discussion last time about this, the block sphere representation of a qubit can have a linear combination of any 2 basis states. And of course, the coefficients of this linear combination are complex numbers and therefore continuous. And so the point is, you can have an infinite number of superpositions, right? There's an infinite number of them because the coefficients of that linear combination are, well, continuous values. But the distinction there about how you come up with this business here, next slide. How is it that we are talking about an infinite number of linear combinations, and yet we're only dealing here with 2 to the 64 possible states with a 64 qubit computer? Well, that's because, once again, that's the number of states before you measure. Okay, it's just simply a superposition of these 2 basis states. But when you make the measurement, the superposition collapses to either one of these 2 basis states. You don't collapse into an intermediate form. The collapse causes it to, when you make the measurement, go into the classical state of either 0 or 1. So that's the whole point. But the power of the quantum computer is that while it's in superposition, it's as if you're in all of these 2 to the 64 states at the same time. And that's the so-called quantum parallelism. And we went through this continued discussion here, the difference between quantum gates and so forth. These words that you have to know, you've got to work on these words. Anytime you see this background slide being a red color, you know that it's something you've got to work on. Then we got into classical computing versus quantum computing. Well, fine. What she meant there is, we don't really have to know quantum mechanics, but it's good to know the basic understanding of what it is in order to be a quantum mechanist. Though if you really wanted to be a proper quantum mechanist, you actually have to understand the physics. And so we start talking about what modern physics and quantum mechanics is. This is a nice map of physics, if you will. Classical and modern physics, what do we have here? Relativity, quantum physics. Relativity could be either special or general, doesn't matter. The point is, as far as we're concerned, very fast. If you're accelerating to very, very high velocities comparable to the speed of causality or information in photons in a vacuum, then it's relativistic, special relativistic mechanics. The very small, though, is quantum, and the marriage of those two is quantum field theory. Leave that alone. We're not going to have to worry about that. So causal determinism is a big deal for the classical physics, and that's the reason why it seems so strange, because we have no direct experience of the quantum world here at the classical macroscopic level of this universe as it is. So there are these basic fundamental assumptions in classical physics, which we talked about, and how it's different in quantum physics. In quantum physics, these are the different realities, if you will, the distinguishing characteristics. We talked about non-determinism, the fact that there's a partitioned theory, what happens before and after measurement. The idea of the wave function collapsing, we haven't defined the wave function yet. And this business about the uncertainty principle, which is, well, it's a characteristic of any wave-like property. And there's 2 ways of looking at the uncertainty principle in terms of uncertainty and position and momentum, or energy and time. You don't really have to know that for this course. That's just stuff you've probably heard of before. We go on to the idea of the Planck unit, and we'll talk about that in a second. We talked about all this. We talked about this too, the quantum BS meter. This is where we really left off. So let's concentrate on this right now. These are really simple statements about the basic properties of a classical mechanical theory and a quantum theory. So we'll go through it again. Particles are point-like objects that follow a predictable, deterministic path, meaning there's an equation that determines the future from well-known initial conditions and boundary conditions as well. And that's not the same in the quantum realm. Okay, particles exhibit a wave-like or a particle-like behavior depending on how you choose to measure them, which is really bizarre. Energy can take on any value in the classical state, but they're discrete values, hence the name in quantum mechanics, quantum mechanics. And then finally, the initial conditions of an experiment repeated many times are the same each repetition, whereas that's not the same in a quantum mechanical system. There's built-in uncertainty from the Heisenberg uncertainty principle and the nature of the wave function itself. Now, I'm going to go through this very quickly here because I don't want to force the history on you. The history of quantum physics. Let's just look at it. It began, believe it or not, when a person called Max Planck was asked to do some research on incandescent light bulbs. All I'm going to say is this is what classical theory predicted, which came to be known as the ultraviolet catastrophe, and eventually a little hack came up with, let's try quantizing energy. And we finally get these black body curves. All a black body curve is well, when you have a light, for example, an incandescent light that's on a that's on a dimming switch, and you just start it. It starts very low intensity light, reddish. And then as it gets brighter, when you put when you increase the voltage, it starts getting whiter and very bright. And then before it blows, what's the color of light when it blows? Blue. So we go from red to blue. Red, low energy, blue, high energy, okay? And so you can see that exactly happens here with these black body curves. That is, of course, increasing energy going down here because the wavelength is getting smaller. Smaller wavelength, higher energy. And so the peak of these curves is going towards the blue end. So the hotter an object, a black body, as they call it for reasons we don't need to get into, the bluer it gets and the more intense it gets. That's why when you look in the sky, only the brightest, bluest stars, with a few exceptions, are the ones you see. So anyway, there's where the origin of, departure from classical theory occurred. However, there's also the photoelectric effect. That's where Einstein got his Nobel Prize, and this idea of bright line optical spectra. If electrons actually orbit a nucleus in a classical sense, they would decay in a millionth of a second. Can someone tell me why? Why would an electron in a classical orbit going around a positively charged nucleus within a millionth of a second decay, just like that? The orbit would be done. Well, it's because the origin of light, or a photon, is from an accelerated charge. And so if you've got an orbital motion, that means that it's accelerating constantly. It's changing its direction, right? Any orbital motion is accelerated motion. And so it would be continuously giving off energy, electromagnetic energy, and therefore it would lose its energy, its orbital energy, and decay. But that doesn't happen. So these three things really were hard to explain. So the photoelectric effect is that photons actually act like particles themselves, rather than just waves, as the double slit experiment was describing. But the big thing is, indeed, this thing here, this slide number 178. Make sure you understand that the Planck constant is the dividing factor. Every quantum mechanical equation has this number in it, okay? And so you should know what the Planck constant is. It's the defining factor for the quantum realm, okay? And really, it's based in this equation, E equals h nu. You saw that in high school. The energy of a photon is related to its frequency via h, which is this Planck constant. But the double slit experiment is the one I want to concentrate on. We keep coming back to it, okay? So let's just look at it. If light were a wave, there's a source. You've got two openings right here in the screen, but one's plugged. You'd expect to see this distribution of well, let's just say if they were particles. If waves were particles, if a photon was a particle, as Einstein included in his PhD dissertation on the photoelectric effect, then you'd expect this distribution on the screen given one slit's open. And if this slit is open and that one's closed, you'll get that one. So you expect the sum of these based on the third law of Kolmogorov's law of probability, which is the basis of probability theory. I hope you all agree that that's what you'd expect. But instead, you get this. And that makes no sense whatsoever if they're particle-like. So they must be wave-like at the same time. But let's just think about this. Here, the nature of the contradiction can be seen even more clearly at dark points. The fact that you see these things here, the fact that you see these, and when they sum together, they don't produce that, but they... Oops, we got a power problem. There we go. Oh, what's going on here? My computer's acting funny. Why are you doing that? Hello, computer. Okay, so instead you see this. Let's read it again. The nature of the contradiction can be seen even more clearly at dark points X, okay? These dark places where individually they weren't dark. This truly defines reason. After all, if the photon has non-zero probability of going through slit one right there, non-zero, if either slit is open, okay, and ending up at X, how can the existence of an additional trajectory for getting to X possibly decrease the probability that it arrives at X? In other words, you know, you have somehow negative probabilities here. They're adding in a destructive manner to produce that dark spot where you'd expect by the third Kolmogorov law. That's basically the three basic laws of probability theory that it's violating it. Does everybody get that? I mean, it's a truly bizarre result. What's even worse is when you start trying to put detectors at these openings to find out, well, okay, which opening did the photon go through? This wave pattern disappears. It's as if, well, that's an act of measurement. That's the problem. Any act of measurement collapses the wave function. We'll get used to that as time goes on. So just to make a long story short, if you read that, the key is we come up with this thing called the wave function, which is an element of the set of complex numbers. Why? Well, we want a probability distribution, but we want one that isn't just additive in normal probability theory. We want something that produces constructive and destructive interference, and the one that works naturally well, it's just a hack. This isn't nature saying, this is what I am. This is us producing a mathematical framework that produces the results. That is all this is. And we call it the wave function so that if you square it, you get the probability. And the mystery of how an assumed particle, such as an electron, can appear to pass through two slits at the same time simultaneously gave rise to a probabilistic wave function, which of course is based on the superposition principle. And if you're interested, that's where Schrodinger's cat came from, which is supposedly purported to be a way of criticizing the notion of superposition, but instead it reinforced it to Planck's horror. Yes, Planck, Schrodinger, all these people, they all came up with these ideas. They didn't believe it themselves, but decades later, it turns out to be true. So let's, this is an important definition here. The wave function is nothing more than a probability distribution that dictates where a particle could be pre-measured. It's before you make the measurement. So that's going to be the basis of our qubit, right? And so it is based on the set of complex numbers, and that means that we can get this interference pattern out of them and a probability at the same time. That's called the Born rule, okay? And the Born rule is this right here. It says that the probability you see a particular outcome is the squared absolute value of the complex amplitude, and you can see that's what's written here in Scott Aronson's paper, which I think I sent out to you. And so this is a nice description. How is it that an electron can somehow go through both of these slits at the same time when it's a particle? Well, here we have the idea of complex amplitudes leads to act differently from probabilities. So the total amplitude of a photon landing at spot alpha, right, is the amplitude of getting through the first slit, alpha 1, plus the amplitude of getting through the second slit, alpha 2. It's just a wave function. And so the probability is the square of the wave function, which in this case is the sum of those two individual complex amplitudes. And you end up getting this. Anybody know what this asterisk could be? Looking ahead a little bit to the mathematics. Well, these are I'm sorry?
Complex conjugate.
Yes, bravo, absolutely. And so there's a nice little example of how this works. But the most important thing to see here is it solves the problem of what we saw on slide 170. Let's see if I can go back. 170. This idea, it's not 170 anymore, is it? Well, anyway, never mind. I'll fix that. I've added too many things to it. Never mind. It's about the decay of the electron orbit. Okay, decay of the electron orbit. So that's what this pertains to. It's not 170 anymore. Sorry about that. I'll fix that, I guess. Anyway, the idea is, okay, we say that, yes, there are many paths where the electron do take these crazy paths, but some have positive amplitudes while others have negative amplitudes, and they end up canceling each other out. That's what we're talking about here. If you accept it here, that's how you keep an electron in a probability distribution or an electron cloud about the nucleus. And from high school, you're already familiar with this. Why is my computer behaving like this? So it's not just my power cord. Too bad. Okay, so in your textbook, page 6, this is what the Born rule looks like. Okay, so basically you have this wave function. Psi is usually used to designate the wave function. Again, this bracket notation, we haven't defined it yet. Be patient. But it is a linear combination of these basis states where alpha and beta are complex numbers, and the square, some square of those gives you the total probability of finding the particle that's described by this wave function. That is an incredibly important thing to keep in mind here, because that is, in fact, a qubit. That is a qubit. So if we could just move past that, the superposition business is nothing more than a probability distribution prior to measurement. And of course, this is not normal probability. This probability allows for constructive and destructive interference. Again, it's a hack. That's what this is. It is something that happens to work. That is all this is. There's no great physical insight buried in here somewhere. You just accept it. Okay, so amplitudes can be negative, which opens up the possibility of interference, and that is key to quantum computing. You can look at this on your own. What's really amazing is if you think, if I can stop for a second. How many people know anything about special relativity? The fact that, well, lengths contract in the direction of relativistic flight, and time dilates. It seems kind of bizarre, doesn't it? Well, those things actually come from the postulates of special relativity. Similarly, what we've just described, you know, if you just accept it, there's another way of describing the double slit experiment in which we basically can rewrite the past. So if you think this stuff, you know, makes perfect sense in the classical frame, rethink it, maybe watch this video right here, but you're not required to do so. It's just to keep people, I'd say, honest about their view of quantum mechanics. Quantum mechanics is very accurate, but very bizarre. So in summary, quantum mechanics is a current model of the microscopic world. Okay, it divides the world into, you know, the observed system, what is it now? As the system and the observer, separated by the collapse of the wave function of partition theory. Okay, a measurement is an interaction between observer and system, and properties of system that can be measured are called observables, like momentum, angular momentum, energy, spin. All right. And the state of the system is represented by a thing called a wave function. It's a vector in a Hilbert space or a complex vector space. We all know what a vector space is. We'll get into that shortly in more detail. Don't mind the fact that, to be pedantic, it's actually an array because the length of these vectors has no physical meaning. But never mind that. Later on next week, we'll talk about a thing called a density matrix. We can introduce that early. That's a different formulation of quantum mechanics, in which instead of dealing with pure states or pure wave functions, we're dealing with mixed states. And in order to do that, we have to get outside of the Schrodinger picture, which is using the wave function. But that's for next week. All right. What else do we have? Quantum mechanics predicts how the state of the system evolves. And that's done by the Schrodinger equation, the pre-measured state. And if you'll recall that Veritasium video we saw, you can see that they actually showed the wave function of a particular particle and how it evolved by solving the Schrodinger equation, which I thought was really cool. The interpretation of quantum mechanics are either deterministic or non-deterministic, and that's not of any concern here. That's just, again, bound to interpretation. The Schrodinger equation describes this evolution. So this is done, actually, instead of solving that partial differential equation, we are describing wave functions as points in a vector space, we perform operations on vectors using transformation matrices, something that you're all familiar with. That is why we use a Hilbert space, or a vector space, or a complex vector space in this case. We use it because it represents this evolution situation rather than solving the Schrodinger equation in a much more elegant and easy to deal with fashion by transformation matrices. Every observable is associated with its own operator. Operations can change the information the observer has about the system and therefore can change the wave function or preserve it. So it becomes sort of an eigenvalue problem. Those of you that, what's an eigenvalue problem? What is an eigenvalue? You people know that, don't you? I sure hope you do. Make sure you do. Make sure you know what it means. First of all, linear transformation of any vector in a vector space means it's rotating and stretching. That's all it does, rotations and stretches. But if you happen to have a problem in which you transform that vector and it doesn't rotate, it just stretches, that's an eigenvalue problem. So all it does, it's like the matrix times the vector equals a constant times the vector, so it's just scaled. That's the eigenvalue problem, and that's very important here. These 2 points summarize superposition and entanglement. You can just read those. They're just summaries. I stress here that, for example, we need to conserve quantum numbers. So, for example, angular momentum or spin. This particle can have a spin 0, and then it decays spontaneously into these two entangled particles. And they have to either be as such or as such, spun this way or spun that way, but they have to be conserved in terms of spin. And so the state of that is still 0. The state of that is still 0. What does that mean? It means that the wave function that describes that now describes two particles. That's what entanglement means. They share the same wave function. You can have them become entangled in other ways too. They don't have to just come from one particle that spontaneously decays into two. You can have two particles come along and interact, and all of a sudden they're both described by the same wave function as well. Now, very briefly, the postulates of quantum mechanics. This is what it's all about, and eventually we'll end up with what they mean for quantum computing. So that's where I learned. This is where you learn this stuff. The problem is you can't really understand quantum mechanics, the mathematics of quantum mechanics, until you've taken this course. It's a third-year physics course called classical or theoretical mechanics. It's the only way. So I'm just going to wave my hands, and when I discuss this, okay, we don't have to concern ourselves with partial differential equations. But we must accept the idea of a Hilbert space for working in these, for evolving the wave function, which will turn out to be a qubit, as we've already described. And so every theory has these three main points. There has to be a postulate that defines the way we describe the state, obviously, and measurements that can be made, the second postulate, and then finally the third postulate, how it evolves. So how do I define the state of a system? How do I define measurement on that system? And how do I evolve the system in time? And so in quantum mechanics, you can think of that as the superposition principle, the measurement principle, and the principle of unitary evolution. There's that word again we talked about last time. Unitary simply means that preserves its unit length. And as I said before, this so-called Bloch sphere is a unit sphere. We'll get to that very shortly here. So make sure you really concentrate on these two slides, 203 and 204. Any questions about those? This is a pioneer of quantum computing at the University of California in Berkeley. You should always look at his notes if you want to get the real thing. All right, so central claim. Okay, the idea again is we have a wave function. It's complex valued and it's probability distribution. It is not the same as classical probability. This explains tunneling. So here's some kind of a potential barrier, right? You know, it could be, so for example, how does fusion work? How does fusion work? How does cold fusion work, even though it hasn't really been demonstrated? I put two protons together. The closer they become, the more they repel each other by the electromagnetic force. It's a billion times more powerful than the gravitational force. But eventually I can overcome that potential barrier through tunneling, okay? Meaning that the wave function of the particle actually is distributed through the potential barrier, and there's a finite probability on the other side of the barrier that you will find that particle. And so when the wave function collapses, beep, you've got tunneling. So that explains tunneling in a nice way. If you've ever heard of plane wave solutions, this is what it's supposed to look like. You're not responsible for that. That's just for those that maybe have a little advanced idea of what the quantum mechanics entails. This is the Schrodinger equation in simple forms. It's a time-dependent one. You can see here, I don't know if any of you have had a third course in calculus where you learn about partial derivatives. Doesn't matter. You don't have to know anything about this, except that there's an I out in front, which is a very strange thing to have in a partial differential equation. There's only a few fields where you will see the complex unit explicitly stated, and you'll see that in the Schrodinger equation. You don't have to worry about this. But anyway, that describes the evolution of the wave function. You see? And what else do we have? The Born rule, which you are responsible for. That's simply how you actually calculate the probabilities. And so these conditions are completely satisfied by associating this wave function as a vector in a complex valued vector space, which is a complete inner product space, meaning what does completeness mean? Completeness means that, you can use calculus because the limit can be applied. In other words, real numbers. Real numbers, complex numbers are related to each other, just separated by the complex unit, I. After all, a complex number is the intersection of the real line with the real line times I, right? And so a Hilbert space is, in fact, a complete inner product space. What's an inner product? An inner product is a generalized dot product. That is all it is, a generalized dot product. So what we're doing with these things called Hilbert spaces is we're taking the power of a vector space, a Euclidean vector space, where you've got the notion of length and distance and measurement and angle, and you're applying it more generally to higher dimensions. And in fact, where instead of just vectors, you can actually use functions as basis vectors. Functions obey the idea of orthonormality. You can make them orthonormal, you can normalize them, and so forth, which is quite amazing. The whole point of this is the use of operators. That's why we use these things, these vector spaces. That's because they really eloquently and in a powerful way represent transformations on states, which are represented as vectors, and the transformation is the multiplication of that vector by a transformation matrix.
I have a question.
Yes.
Are the functions you described, are they all the linear transformations?
Oh, no. I'm talking now about, we haven't got there yet. Okay. I'm saying functions can actually be vectors. Functions behave as vectors. And so you can come up with a thing, instead of a vector space, you can generalize it as a function space, because functions actually obey all of the properties of a vector space. And so you can use an orthonormal basis set of functions to describe a space of functions, which is extremely powerful. And that's what, in fact, we are doing here. I'm not sure if that answers your question. Maybe we should wait till we get to the next PowerPoint, which is coming up soon. Does that answer you? I hear nothing. Hello?
Sorry, I'm reading it.
Oh, okay. Is that all right for now?
Yeah, thank you.
Okay. So what we have now is a Hilbert space is a generalization of our 3D world. Just look around you right now. Look around you. This is a Hilbert space. You live in a Hilbert space. It consists of vectors which behave as we expect them to behave, together with a dot product, or we can generalize it as an inner product, defining vector lengths, distances, angles, and an overall geometry that is intuitive as extensions of our 3D world. It's quite powerful. From the point of view of a Hilbert space, advanced constructions such as Fourier transforms are intuitive and simple. What's a Fourier transform? We talked about that last time. We'll talk about it again when it becomes important. Anywhere, not only in quantum mechanics, where one deals with operators, the space on which these operators operate must be specified. Otherwise, one would be dealing with undefined objects. So it's the whole reason why we use vector spaces is because of linear transformation theory, which is solely related to operators. And so here, looking ahead a little bit, Dirac's bracket notation, right? A bra and a ket, is a simplified syllabary for the calculus, really. It's the language of Hilbert spaces, and inner product space is quite complicated. And in fact, he came up with this in the 1930s, this notation which greatly simplifies things. You have to go along with it. So we have right here a ket. Okay, this is a ket. You see this part right here. The ket is a vector. Okay, it's a vector in a Hilbert space. The magnitude of the ket is meaningless. That's why it's a ray, really. And this thing that's inside is merely a label. We'll discuss it further as time goes on. In fact, I've just sent out what's basically a PDF, mostly based on Wikipedia. Wikipedia does a great job of describing bracket notation. So we'll get to that in a second. So thus far we have stated the formal requirements for a state function and its evolution. We need to still specify measurement, and how about multiple qubits? In other words, we have to have composite quantum systems. We need to have more than one qubit, clearly, to do anything meaningful. All right. So let's just go forward. This is what they look like. This comes from the University of Waterloo. This website right here gives you a free download of what I consider to be one of the better descriptions. You're not required to look at it, but it's an excellent summary of the mathematics of quantum computing. If you're not sure, I'll tell you right now, the University of Waterloo is one of the world-leading institutions in quantum computing right here in Canada. But anyway, these four postulates are generally what we use. The number of postulates of quantum mechanics varies usually from 3, 4 to 6, 8, but let's just stick with these four. One is a complete description of the state, okay? That's statics. You've got this thing sitting there. Its dynamics, how it evolves, is determined by the Schrodinger equation. And interactions, by measurement, I mean, is dictated by the Born rule. And so that gives us our notion of measurement. And composite systems is done with this weird thing called a tensor product. Now, some of you might think, okay, we've had an inner product. I suppose the next thing, which is like the dot product, well, we're going to have something like an outer product, which is like the cross product. You'd guess that, wouldn't you? But it is not the cross product. It's actually something you probably never heard of. It's called the exterior product. So inner product, exterior product. And that's what we're going to use here. The outer product, or based on the exterior product, is actually also called the tensor product. Oh boy, oh boy. And that's where I want you to just relax. Here, these four postulates specify a general framework for describing the behavior of a quantum system. Here, that's clearly an eigenvalue problem, right? This is taking this vector, you operate on it with this Hamiltonian operator, you don't have to know what that means, and you have this energy eigenvalue. You're projecting that vector, right? You're changing, you're projecting. An eigenvalue problem is one in which you're not rotating, you're just going along a straight line, and that's what we're doing here. But the whole point here is there's a fifth one, not just these four, but this fifth one. Physical observables are represented by the eigenvalues of a Hermitian operator on the Hilbert space. What the heck is that word right there? The two operators you have to really be well aware of are unitary operators and Hermitian. And so, Hermitian operator in quantum mechanics, operators play a unique role as the observables. Physical quantities which can be measured are represented by them. It is assumed that the measurement of a physical quantity must yield one of the eigenvalues of the operator. They have to be positive. Now, sorry, they have to be real. That is what a Hermitian operator is. It's one that produces real numbers, and that's what we need when we're making measurements. You're not going to measure a complex number. Since the observables are always real, the operators representing them must be Hermitian. Make sure you know that. That is all that word means right there, and you'll see it over and over again. So for quantum computing, you can turn these four postulates into the following. The definition of a qubit is the first one. How qubits transform or evolve unitary evolution. So you're applying unitary transformations before you make the measurement. When you measure them, you apply a Hermitian operator. And how you put them together, that's the multi-qubit principle. Unitary operations conserve probability before you make the measurement, right? And so that makes them time reversible. That's why we talk about reversible operations. We're going to have to take a break soon. The measurement principle. The act of measurement of a quantum system depends on the conceptualization of quantum mechanics, that collapse business, okay? And that's what we call the Copenhagen interpretation. This is just a side note, okay? We don't even know what that means, but you can go back and look at this reference. Geez, I wonder if that slide's changed now. Anyway, the one where there were these three reference videos you could look at as to the problems of interpreting quantum mechanics. You don't have to worry about that. It's a side note. So the collapse of the wave function in the measurement problem here has never been observed. We don't know what that means. Now, this part here, complete summary of key points in quantum mechanics. This is, you see it down here, FYI. You're not responsible for this. This stuff right here is for those of you that have had maybe a little bit of quantum computing in your high school education. This, on the other hand, you are responsible for to a point. There are alternative formalisms for the dynamics. So that's this part here. Now that you've got these four basic postulates, the dynamics part has three different interpretations, okay? Three different ways that you can formalize this. One is called the Schrodinger picture. That's the one we use. The other is the Heisenberg picture and the Dirac picture. It turns out you don't have to know that, but that's what they mean as far as the operator theory is concerned. Don't worry about this. This is just there for completeness. The reason why I'm putting this here is because eventually, even though we're using the Schrodinger picture all the time, eventually we're going to have to use the density matrix, and that would be next week. Just for a brief part that involves mixed states. Don't get too carried away with this. And when I gloss over things like this, you know that I'm not going to make you reproduce this table. You know, don't worry about it. You know, trust me. And so the density matrix or density operator has to do with mixed states as opposed to pure states. Mixed states are what we usually have to contend with in real quantum mechanical measurements and hence real quantum computers, okay? Never mind that. You've all seen that, I hope. So in summary, computations based on classical physics appear to be giving way to quantum-based computations, right? Quantum physics is not like the classical realm. Key concepts, information, the theory of computation, computational complexity in particular, fundamental notions of quantum mechanics, and eventually the mathematics, which has to do with Hilbert spaces. There's a nice conceptual summary. So for these appendices, read this one on your own, Scott Aronson's view. We basically talked about that already. About, this proof of quantum time reversibility, that is completely, as you see here, for your information. That's just for those of you that are fairly advanced. Appendix 3, on the other hand, this is something I want you to look at from time to time. Linear superposition, quantum parallelism, and entanglement. What's that other one there? No cloning theorem. We're going to talk about those things. Entanglement and non-factorable superposition. What does that mean? We're going to get into that. Communication at superluminal speeds is not possible. A lot of no-go theorems we're going to get into. Qubit, Bloch sphere, no teleportation theorem, quantum teleportation, no deleting theorem, no cloning theorem, no broadcast theorem. This is looking ahead. These are the things we have to know. Olevo's theorem, superdense coding, communications channels, channel capacity, unitary operators. These are nice things I want you to know. Shor's algorithm, that's where we're headed. You already know something about that. Okay, and quite frankly, that's superdense coding right there. You could read that on your own if you want, just to jump ahead of the curve. I like to throw a few things ahead. You can look at that and we'll talk about it later. These are great resources as far as terminology goes. These two websites, if you're not sure what something is, go there. And that's that. And if you're kind of stuck on linear algebra, this is a nice place to look. Whatever. That's nice too. That's that Waterloo piece I told you about. You can see they have a nice summary of complex variables, a nice summary of matrix algebra, things you should know, and of the mathematics of quantum mechanics. And that's that for now. Maybe we should take a break. Let's start up at 10:30, okay? Everybody good with that?
Yep, sounds good.
All right, 10:30. We'll see you in 11 minutes.